Baby shawties, how we doing? Welcome to our next video lesson for current electricity. Today we're going to focus on what's called electric power. So electric power is going to be looking now at the components within a circuit. So we talked about the relationship between the three important details: voltage, current, and resistance. Voltage is obviously produced by the energy source, which is normally the batteries or outlets or whatever it might be. They're going to produce that flow of charge, which is called the current, and then that current is also going to be related to how much resistance there is in a circuit, and that the current produced is going to be a relationship or ratio of how much voltage there is in a circuit to the overall resistance. What we're going to talk about today is the idea of power. So this is actually a unit or a concept we talked about back with energy. Power, when we did, like, for example, the physics Olympics, it was how much work you could do, how much energy that you could consume or utilize in a certain amount of time. And this is something that we can also relate back to electric circuits, because the whole idea is that our voltage source, the batteries or the outlets, are supplying the energy, but the whole purpose of building a circuit is that we can utilize or use the energy that we are supplying to charge. So when looking at power, again, it's going to relate the idea of voltage and current within a circuit. Each component within a circuit is going to utilize the energy that's provided by the voltage source. So we talked about and we looked at things like if we had a single light bulb versus 3 light bulbs. Should have noticed some of the things like the current dropping and things like that. But the idea is that the amount of energy used by something is going to depend on 2 things. It's going to depend on the voltage. And the voltage is going to be how much energy is actually being supplied by the voltage source to that individual component. Okay, it might be all of the energy, so let's say it's 9 volts. It might be all 9 volts, or it might be, if there's multiple components within the circuit, it might be a part of that 9 volts. And it's also dependent upon the current. The current is going to be the flow of charge that's actually moving through the circuit. And that's important because in order to supply the energy to, let's say, the light bulb, charge needs to flow throughout the circuit. We need that flowing charge to actually go through that component or that device in order for energy to be supplied to that object. So essentially it's going to be these 2 things, current and voltage, that's going to produce the amount of power. Okay, and just remember that as we calculate power, the unit that we're always going to use is what's called a watt. And relating this back to energy, a watt is 1 joule of energy used every second. So it's, again, going to look at the amount of energy that object is using through a certain amount of time. Okay, and this is only applied to when we actually are using that energy when that device is actually turned on. All right, now this is something, again, kind of putting everything together. This is stuff that you see, might not have actually looked at, but stuff that we utilize every day. So power is kind of the more important thing. So this is the label for a coffee maker, okay? So I just want you to notice this part down here, kind of in the middle of this tag. This is actually where you get all the information about this coffee maker. And I want you to notice a couple things. So the first thing is that I want you to notice here it says VAC. So this is voltage. So I want you to notice that this thing needs to be plugged into a standard 120 volt source. When it does that, it's going to, when turned on, you'll see here amps. So amps is the current that's produced. So notice we have voltage and we have current. When that current is produced, it says here that it's going to draw about 19.5 to about 25.8 amps. So there's a little bit of range depending on maybe whether it's just heating the coffee up, whether it's brewing or what have you. And then you'll notice here it says kW. Now kW represents kilowatts. Okay, so that is kilowatts, so that's 1,000 watts. But you'll see here that when this coffee maker is being used, it's ranging between about 4.6 to 9.1 kilowatts. So let's say, just choose a value within that range. So let's say it has 5 kilowatts. That means it's about 5,000 watts of power. So again, 5,000 watts means that it's going to be using 5,000 joules of energy every 1 second that it is being used. Okay, so that's a large amount of energy that's being used by that coffee maker. But think about, it takes water at a normal temperature and brings it up to a nice hot temperature, and it does that through a process. Okay, so just wanted to show you here how voltage and current and power, all these things are related in terms of the devices that we are using. So I bring up that label on an appliance is because wattage is something we see all the time. So wattage is probably a term that we've heard before when it comes to appliances that we use every day. One common appliance that we use every day that we see wattage is a light bulb. Okay, there's three different types of light bulbs that we use. There's incandescent bulbs, there's CFL bulbs, and LED. CFL means compact fluorescent, LED means a light emitting diode. Each of these bulbs act differently. They're all about the same in that you have, the bottom and the side endpoint that you need to connect on all of these bulbs. Okay, but the idea is that each of these bulbs is going to be rated with a certain wattage. You'll see here the incandescent bulb has 60 watts versus the CFL 14 watts versus the LED, which is 12 watts. The obvious difference there is that the wattage for the incandescent bulb is much greater than these two. And comparing the CFL and LED bulb, you'll notice that the LED bulb is even less than that, okay? Wattage describes, again, how much energy they're being used. Now, the whole purpose of, obviously, a light bulb is to emit light. So down below kind of just shows kind of a comparison of these three bulbs. All right, so why I brought these three bulbs up is because the brightness of all three bulbs, we'll talk about that in a second, in terms of what's called a lumen, notice they're all the same. So in terms of the light that they're producing, these bulbs are all going to be the same. But here's the difference when it comes down to wattage. Wattage is describing how much energy these things are using in order to produce that light. So a 60 watt bulb, obviously in terms of wattage, uses a lot more energy than those other bulbs. Now, why does that matter? Is because energy relates then the cost. Then in order to run this bulb, let's say for an entire year, it's going to cost us around $13 versus these bulbs are going to cost considerably less, okay? Because the wattage means that we're not using as much energy, which in terms of cost then means that we're not going to be charged as much. And then there's some also benefits because we're not utilizing it as much energy and because the process in each of these is the same, is down below it has the lifetime. An incandescent bulb, if we were to run it continuously, would only last for about 750 hours. That's not much time. A CFL bulb, okay, it would be 10,000 hours, which is much better. And then you have an LED bulb, which if you were to run it continuously, could last up to 5 years on a continuous light. So LED bulbs not only are energy efficient and create a good brightness comparable to other bulbs, but they also last a lifetime, which is why nowadays you'll see LED bulbs being used primarily over incandescent and even CFL bulbs. So all bulbs are going to be different in terms of how they produce the light as well as the wattage that they're going to use. Another thing you're going to see with light bulbs, and this is something that as you get older and you have to actually start buying bulbs, if you ever own your own place or whatever it might be, is that you'll see this kind of label shown on the box of all light bulbs. Again, so they'll show you, again, the wattage of those bulbs, the light appearance, that's whether it's a nice soft light or maybe it's more like daylight, the lifetime, so you'll see that if you use it for 3 hours a day, it's going to last you 9 years, the estimated cost, and then another big thing which is compared to the power rating is the brightness. Now the brightness, what we do is relate a unit called a lumen. Okay, now a lumen is just, think of the word luminous or luminosity, if you've ever heard of that before. It means when things light up or are bright. So you'll see that unit being used to describe how bright a bulb is. And there is a relationship, a mathematical relationship for the different types of bulbs between wattage and lumens. But you'll see this label there. So again, power is going to be describing the energy usage of those different devices. All right, so the idea is if we connect these variables, we talked about that obviously there's voltage, current, resistance, and now power. Voltage, again, is the energy being supplied by the batteries. So say I have here 2 batteries having each 9 volts. I know that total there's going to be 18 total volts supplied to the circuit. That voltage is going to produce a current. Okay, now the current, 1.8 amps, is also going to be based upon the resistance within the circuit, which we see as 10 ohms. So there's a relationship there between the voltage, current, and the resistance, and that's this Ohm's law we talked about in our previous section, okay? Now, based upon those things, you'll notice the brightness of the bulb. So notice how it's shining much brighter, okay? And that is because if we think about the brightness, that is going to be the energy being used by that bulb, and that's what's relating to the power. So notice here that the power, I can think about, okay, here's the current being supplied, and then we also have to look at the voltage that's actually being utilized by the bulb. Now the idea is this: 18 volts is supplied by the two batteries. What we're going to start to look at is how much voltage is actually used by the bulb, okay? And that's where power comes into play, because if I add in here a second bulb, you'll notice that, okay, if I add a second bulb being identical to the first, notice first that the current drops. So the current drops because as I add another bulb, I'm adding more resistance. But at the same time, you'll notice that the brightness represented by those starbursts, that the brightness actually decreases as well. So all these variables are related, okay? The voltage, current, resistance, and power. Think of each of them individually. Voltage is the energy being supplied. Current is the flow of charge. Resistance is exactly what its name says. And then power is the energy being used by each device. So what we're going to do next is we're just going to look at the mathematical relationships for this. And then you guys are going to be doing another lab simulation that's going to be looking at the relationship between all four of these four individual components. So let's just say that I had one of those 60-watt incandescent bulbs, if you will, plugged into a 120-volt source. So all objects or devices are going to be rated based on a wattage, and a wattage describes how much energy they're being used. So notice here I have the energy being used by that device as well as the voltage that's being supplied. So to find the current, I'm just going to use the relationship power equals current times voltage, P equals IV. I know that the power is 60 watts, current is what I'm solving for, and my voltage is 120 volts. So if I were to solve for current, all I need to do is divide by 120 on both sides, and that would give me a current of 0.5 amps, okay? So it produces a current based on the energy being utilized by that object as well as the energy being supplied. So now let's say that instead of a 60-watt bulb, I now plug in a wattage 120-watt bulb. So 120-watt bulb means it's going to use more energy. Okay, heck, this might affect its brightness as well. But that means if it needs more energy, we still have that 120-volt source. Let's see what happens here. So if I now have 120 watts being needed, and it's still plugged into a 120-volt source, now notice when I solve for the current by dividing by 120 again, I'm going to get a current equal to 1 amp. So notice that when the power rating of that object is higher, it's going to draw more current there, okay? The idea is this, is that power is the energy needed for that thing to be, powered, and that thing to work. So what happens is that since charge is the energy carrier, if the thing needs more energy, I need charge to move faster through that object, okay? Especially when my voltage source is 120 volts. If that stays constant, the current is going to have to be a lot faster in order to get the energy to that object that I need. All right, next couple examples we're going to look at is now just kind of flipping the relationship. Now, okay, if we have a voltage source producing a certain current, how much power is that going to actually supply to something? All right, so let's say that I have a saw that draws 12 amps of current when plugged into a 120-volt outlet. So real quick, think about the last couple problems. 12 amps is a large amount of current plugged into that same 120-volt standard outlet. That means if I see that much current, this has got to be a pretty large power rating. So what we're going to do to find the power rating again is we're going to take just the current times the voltage. But now you're given current and voltage, so this should be pretty consistent. I'm going to take 12 amps of current times 120 volts, and that's going to give me a power of 1,440 watts, which means that that saw is going to use a lot of energy to actually cut things. Same thing now, notice I have a toaster. Okay, so a toaster draws 6 amps of current when plugged into a 120-volt outlet. So 6 amps, again, is a pretty large amount of current, but if I want to find the power rating in watts, I'm going to take the current times the voltage, so 6 amps times 12 volts, and that's going to give me 720 watts. So again, that's going to be a lot of energy being utilized by that saw and by that toaster. So power, again, is going to be related to the current and the voltage. First two examples, we looked at what happens when we produce, if we know the power rating, how much current is going to produce, but now if we know the current and the voltage, we can talk about the power that it's actually going to be utilizing. All right, example 2 here, what we're going to look at is now throw in the concept of resistance. So notice when I gave you guys that label of voltage, current, and power that was shown, notice resistance was not on there. But all devices are going to have a certain amount of resistance. And here's the idea. If we need to draw more current to that object, its resistance is going to be less. If we're going to draw a small amount of current to that object, that means it's going to have a higher amount of resistance. So it follows that same idea that current is dependent upon the resistance. So we can use resistance to control what's actually going on in the circuit. So now I want to kind of look at the same thing. Let's say that I have a 1,000 watt microwave that's plugged into a standard source and it has a resistance of 14.4 ohms. What is going to be the current that it produces? So it's very similar to what we did in the first example here, except in this case I'm not giving you the voltage, I'm giving you the resistance of that object. Now, in order to do this, I have to use both my relationships that we know at this point. So I know that current is the ratio of the voltage to the resistance, okay? And I know that power is the current times the voltage. So here's the ideas. And in order to figure this out, I need to somehow relate power, current, and resistance all in one. So here's what I'm going to do. I'm going to take this first equation, Ohm's law, and I'm going to rework it a little bit, okay? What I'm going to say is this, is that the voltage is going to be equal to the current times the resistance. To do that, all I'm going to do is multiply this bottom by R. And what I'm going to do is use the second equation, power equals current times voltage, and to relate these two things, current and resistance, I'm going to take this chunk right here and I'm going to substitute it in where voltage goes. And what I would get is this, that power is going to equal the current times the resistance. To simplify that, I'll say power is equal to the current squared times the resistance. So this is one way that I can use the two relationships to try and figure out what that current is going to be. Now, plugging things in then, I know that my power is going to be 1,000 watts. The current is what I'm solving for, and my resistance is 14.4 ohms. So we're going to require a little bit more algebra here, so I'm going to have to first divide by 14.4 and then take the square root. But when I do that, when I get my current, I'm going to get about 8.3 amps. Okay, so I'm going to skip the algebra there, but again, I'd have to divide and then take the square root, and that's the current I would get. So notice I'm drawing a pretty good amount of current from that 1,000 watt microwave, but notice the power rating that it has and then the resistance. This is like almost the resistance of a light bulb for that 1,000 watt microwave. All right, so now I want to know what would be the power rating of a 15 ohm toaster that draws 8 amps of current. So with this one, again, I'm going to use my two relationships. Now I know 8 amps, which is my current, 15 ohms, which is my resistance. Now, what I don't know, again, is my voltage. But if I want to solve for power again, P equals I times V, okay, what I do know now is from the last relationship that we can also relate this to current and resistance by looking at I squared times R. So if I just simply type in or plug in my current, which is 8, times my resistance, which is 15. The only difference here is that I have to square my current. It should give me my power rating in this case, which is going to be 960 watts. Okay, so again, this is a way in which we can relate the current and the resistance to the power rating of those certain devices. And this is going to lead us to our last example here, and this is what you're going to be doing in the lab simulations. Now we're going to relate all 4 of these variables, voltage, current, resistance, and power, but we're going to look at the individual components. So what I have here is just kind of a snapshot of the simulation to show some of the values that we have. So you notice I have here 2 9-volt batteries. I have 3 bulbs attached, each 10 ohms each, and then I have my ammeters here to show the current going through those bulbs. Now the purpose of this is we're going to look at the 4 variables, voltage, current, resistance, and power. So voltage would be how much energy is being supplied to each device. Current would be how much current or charge is flowing through each device. Resistance, what's the resistance of each device? Power, how much energy is actually being used in terms of watts by each device. Okay, so I'll start with some of the things that I know. I do know, for example, the voltage of the battery. I have 2 9-volt batteries, which hopefully you remember is 18 volts. Okay. I am showing the resistance of all 3 bulbs. I know the resistance is all 10 ohms apiece for each of those. Okay. And then you are given the current going through all 3 bulbs. We know that the current is going to be 0.6 amps for all 3. Okay? So what our goal is we're going to try and fill out the rest of this table. To do that, we're going to need to know the voltage and power. Now, voltage, again, is going to be the energy supplied to each component by the battery. And then the power is going to be the amount of energy that object is going to use when it's actually plugged in. So we'll start off first with the voltage. Okay, so voltage, again, we're going to use that relationship that current is the ratio of voltage to resistance. Now, what I did in the previous examples, I rewrote this, that voltage can be found by taking the current times the resistance. So for example, if I take these two things, current times resistance, and multiply them together, I'm going to get the voltage. So if I take 0.6 amps of current times 10 ohms of resistance, multiply these two, I'm going to get a voltage of 6 volts. Same thing for the other two bulbs. I would get the same identical value because they are all the same current and same resistance. Now I want you to notice one thing. The battery has a total of 18 volts. That's the amount of energy it's supplying to the entire circuit. And notice that each bulb has 6 volts of that. And why it's important is because if you were to add up all three of those numbers, notice that would give you 18 volts. So the energy being supplied by the battery here is being divvied up to each of those individual devices. Okay? All right, then to find power, if I want to find the power utilized by each of these bulbs, what I'm then going to do is just take the current times the voltage. So I would take 6 volts times my 0.6 amps, and that would give me then a power rating would be about 3.6 watts for the first bulb, as well as the other bulb since they all have the same. Okay, so notice again that the power for each of those is going to be the same, 3.6 watts. Represents the amount of energy being utilized by those light bulbs every second. Now what we can relate this then to is notice that the wattage, we can compare that to the brightness. So you notice that those three bulbs based on the starburst are not that bright of bulbs, so we know that it's not utilizing a lot of power, a lot of energy. Okay, now the only thing to think about is that if we look at then the current, resistance, and power, the battery is the only thing we're missing. So the one thing to think about is that current, remember, is the flow of charge throughout the entire circuit. And one thing we did talk about is that the current that flows through this is the same throughout. Meaning the current that's going through the first bulb, second bulb, third bulb, notice they're all the same, would be the same as the current flowing through the batteries. So that 0.6 amps would be the same for that battery. Now to figure out the resistance, again, we can use the Ohm's law relationship that the current produced I equals V over R. So if the overall voltage within this circuit is 18 volts, my current is 0.6 amps, what sort of resistance would create that current? Now using some algebra to solve for R, I would just have to take the 18 volts and divide it by the 0.6 amps. And if I did that, I would get 30 ohms of overall resistance. Now that's not the resistance of the battery, but what that represents is the resistance within the circuit, kind of like the total resistance. And notice that if I have 3 bulbs, notice that all those resistances are adding up to give me 30. And then the last thing we want to do is find power. So power, again, is the voltage times the current, so 18 times 0.6, which would give me a total of 10.8 watts. Now, why that is neat as well is, again, if I were to look at my values, if I were to take 3.6, which is the power used, or the power for each bulb, which is the energy used by each bulb, notice that it adds up to the energy being used throughout the entire circuit, so 10.8 watts. Kind of subtle but what this is showing is actually a little bit of conservation of energy. That notice I have the energy supplied by the battery, energy utilized by each object. I have the power rating of the entire circuit of the battery, representing then the power rating of each object, how they add up. Okay, so this is kind of relating the ideas of voltage, current, resistance, and power. We have really 2 formulas, but we're relating all these ideas, energy being supplied to create the flow of charge, controlling charge through resistance, and then utilizing that energy in the form of power for each device within our circuit. Okay, so if you guys got any questions, make sure you jot those things down. Otherwise, you have your little lab simulation you're going to do connecting all the variables of voltage, current, resistance, and power. Good luck, guys. Peace out.